Hello everyone. Now we'll be discussing k-means cluster analysis. This is a non-hierarchical clustering method. We will see the procedure and then we'll solve one example. Okay. So k-means cluster analysis is this k denotes the number of groups that we want. The difference between hierarchical and non-hierarchical methods we have already discussed in the introductory lecture. So here at every stage we are going to have k clusters and there will be reshuffling. Okay, there will be a lot of reshuffling. So unlike hierarchical, even if two objects are in two different groups at one stage, they may combine at next stage, they may again get separated in the further next step and so on. Okay, so what is the procedure? Let me write down the procedure. Initially, we start with k random seeds. What do I mean by seeds? So if we are talking of the p-dimensional data, if the observations that we have are p-dimensional, then we choose p-dimensional vectors roughly around in the same range as that of data. So for example, if you have bivariate data set and if the scatter plot looks something like this, then you may choose 2 points in the range, say for example this and this, as two different seeds. Okay, so you have to choose points which are roughly in the range of the data, but as far as possible they are away from each other. So 2 if you want 2 groups, you will select 3 points if you want 3 groups and so on. Okay, so depending on the number of groups you want, we will choose the seeds. So we want k groups, so we would choose k seeds. Then compute distance of each observation from each of the seeds. Compute distance of each observation from each of the seeds. Okay, so what happens because of this? Because remember the difference. In hierarchical clustering, we were computing distances between the observations, whereas here we are not computing distance of one observation from other. We are computing distance of each observation from each seed. So if I have seeds S1, S2, Sk, then and observations O1, O2, On, then I'll get such n cross k table. Okay, I'll get n cross k table of distances. Then what we have to do? For every observation, locate the seed to which that observation is closest. Okay, for every observation, locate the seed to which that observation is closest. Okay, so what do we mean by that? In this table we talked about, we have to locate minimum in every row. So for O1, which of these k entries is minimum? Suppose second entry is minimum. Then we will say for O1, seed 2 is the closest one. Similarly for O2, we will say in this row, which entry is lowest. And we will say, okay, that seed is closest to this observation. Okay. And then, as per that closest seed, you assign observations. Okay. Locate the seed to which that observation is the closest and allot an observation to jth group if it is closest to jth seed. Group means cluster. If it is closest to jth seed. Okay. Allot an observation to jth group if it is closest to jth seed. Then you do this for every observation. So at the end, now you will have k different groups. Because there are k seeds, you will have k different groups. Now compute the mean of each of these k groups. Okay, compute the mean of each of these k groups, and these mean vectors would now become new seeds. So use these mean vectors as new seeds, and then use these mean vectors as new seeds, and then repeat steps 2 to okay, let me write this as a separate step. Now repeat steps 2 to 5 till we get 2 consecutive, till we get same grouping in 2 consecutive trials or iterations. Same grouping in 2 consecutive iterations. Okay, so this is sort of conversions that we are looking for. So if we get same grouping, then obviously we'll get same groupings, means if every observation goes to the same group as it was in the earlier iteration, then we will get exactly same means. So even repeating this analysis won't change any final result, and the process would converge. Okay, so this is a k-means procedure. At first some people feel it's kind of random, but see, even if we start with random seeds, after first step what we are doing is we are computing mean of each cluster, and then we are checking whether the observations which are already in that cluster, are they still good to go, means are they still closest to the mean of that cluster, or are they closer to mean of some other cluster. If they are closer to the mean of some other cluster, we shift them there, and we go on doing this till this configuration stabilizes. So we are finally trying to allot everyone in a group in which it actually fits. Okay, so this is the k-means clustering procedure. Of course, as you might have realized, this works only on the continuous observations, because you can't compute mean for categorical data. For categorical data, you can have exact similar thing, but with modes. So it would be known as k-modes clustering. Okay. The choice of seeds does cause some changes in the final result. So some people, what they do is they try with 2-3 different sets of seeds, and then sort of try to see if the results match or not. Okay, so let us try to illustrate this with one example. We'll take some small bivariate data set, and we'll take, say, Manhattan distance, so that we don't have to worry about taking square root, because in Euclidean distance we'll need square root. Okay, so let me take 5 bivariate observations. So suppose 1 0 0 1 2 2 1 1 and 1 2. These are 5 observations. Let me call them O1, O2, O3, O4, O5. Okay, and I want to suppose do 2 means cluster analysis. 2 means cluster analysis means I want to divide them into 2 different groups. Okay, so I have to start with some random seeds. So let me take seed 1 as 0 0 and seed 2 as 2 2. I can take one of the observations as seed, that is allowed. Okay, now let us compute distance of each observation from each of these seeds. Okay, so distance of O1 and S1 would be, as I said, we are using Manhattan method, so 1 minus 0 in modulus plus 0 minus 0 in modulus. So the distance is 1. Here it would be 1 plus 2, so 3. Okay, how am I doing this? Absolute of 1 minus 2 is 1, and then absolute of 0 minus 2 is 2. So 2 plus 1 is 3. Then distance between O2 and S1 would again be 1. Distance between O2 and S2 would again be 3. O3 and S1 would be 4, 2 plus 2. O3 and S2 is 0. O4 and S1 is 1. O4 and S2 is also 1. O5 and S1 is 1 plus 2, 3. And here it is 1. Okay. So O1, for O1, S1 is closest. For O2, S2 is closest. For O3, S2 is closest. For O5, S2 is closest. Here I have a choice. O4 I can either send to S1 or S2. So for the time being, let me put it in S1. Okay. So now at this stage, at the first step, my clusters are, so cluster 1 is O1, O2, O4, and cluster 2 is O3, O5. Okay. Now I have to compute revised seeds. So seed 1 is mean of cluster 1. So cluster 1 means I have to take mean of O1, O2, O4. So O1 is 1, 0. So mean of O1, O2, O4 would be 2 by 3 and again 2 by 3 actually. So 2 by 3, 2 by 3. That would be the mean vector. So let me write down. It would be 2 by 3, 2 by 3, and mean of C2 would be S2. So S2 is supposed to be mean of O3 and O5. So 3 by 2 plus, comma 4 by 2. 4 by 2 means actually 2. Okay. So let me write 4 by 2 as 2. Okay. Now with these new seeds, I have to repeat this whole exercise. So let me compute distance of each observation from each of these new seeds. S1, S2, O1, O2, O3, O4, O5. Now distance of O1. O1 is 0, 1 or 1, 0. Let me confirm. O1 is 1, 0. So 1 minus 2 by 3 is 1 by 3 and 0 minus 2 by 3 is 2 by 3. So 1 by 3 plus 2 by 3, so the distance is 1. Okay. 1 minus 3 by 2 would be half and then 2. So 2 plus half, so 2.5. Then O2 is 0, 1. So the distance would be 2 by 3 plus 1 by 3. So again 1. And here distance would be again 1 by 2 plus, 3 by 2 plus 1. So again it would be 2.5. O3. How was O3? Let me check. O3 is 2, 2. So 2 minus 2 by 3, 2 times. Okay. So it is 8 by 3. 4 by 3 2 times. So it is 8 by 3. And here it would be 2 minus 2 would be 0 and this is just 0.5. Okay. O4 is 1, 1. So 1 minus 2 by 3, 1 minus 2 by 3. So it would be 1 by 3 plus 1 by 3. So basically it would be 2 by 3. Here it would be 0.5 plus 1. So it would be 1.5. Okay. And in the last observation is 1, 2. Right? 1, 2. So 1, 2. So 1 minus 2 by 3 is 1 by 3. And from there 4 by 3. So 4 by 3 plus 1 by 3. So we'll have 5 by 3. Here 5 by 3. And here 1, 2 means this is 0. So from here only 0.5. So 0.5. Okay. So here this is closest, this is closest, this is closest, this is closest, and this is closest. So I get O1, O2, O4 in one group, O3, O5 in other group. So this is exactly same as the earlier configuration. So my cluster analysis procedure has converged. So we stop here. Okay. So this is how we carry out k-means cluster analysis. Now one advantage of k-means cluster analysis over hierarchical is that computationally it is less intense, because the size of the distance matrix that we are storing is n cross k, and most of the times k is pretty small. Even if you have like 50,000 observations, you may be interested in getting say at most 50, 60, 100 groups. You won't be getting like 25,000 groups. Whereas in the hierarchical cluster analysis, you will start with 50,000 cross 50,000 distance matrix, and every time you are replacing, but still in the initial stages your distance matrices are going to be pretty big. So computationally it is very heavy, and you need computers with very good processing power. Okay. Whereas in k-means that problem is not there. So that way for large data sets generally k-means is preferred. About the choice of seeds, generally, as I said, the choice of seeds does affect the final result. So what people do is sometimes they, if the data set is small, then they carry out hierarchical clustering first. From hierarchical clustering they get k groups, and then take means of those k groups as the initial seeds. Okay. So this is all about k-means clustering. We'll try to discuss the practical aspects of it in the next lecture. Thank you.